baby. Extra bright, I want y'all to see this. Turn up the lights in here, baby. You know what I need, want you to see.
Light. It makes reading easier in the dark. It also makes driving at night possible. And it also makes for a very good argument that has lasted for almost 300 years. Now scientists and physicists have been arguing from Newton to Einstein that light is a particle. However, some say light is a wave. And then you have that random scientist who says light is an electromagnetic wave. What? Anyways, believe it or not, but I'd rather you believe what I'm saying because it's 100% correct, is actually both. Now that is hard to believe because that's like saying someone is pretty ugly, which is an oxymoron, but that's for English class, we're in physics. But scientists have thought of the theories that have proven both cases. However, I'm here to talk about how the particle nature of light came about. So keep your head up, eyes open, and prepare yourself for this wonderful journey I will take you on, in which I will prove to you that I'm right. Let's start off with the beginning of the arguments and theories. Around the time 1700, Sir Isaac Newton concluded that light was a group of particles, which was known as the corpuscular theory, and that theory had stuck around for quite a while, because who was going to argue with the guy who invented force equals mass times acceleration? Newton believed in the corpuscular theory because light traveled in a straight line, and it was obvious to Newton to go in that straight of a line, particles had to be involved. But his theory could not explain the wave-like phenomena such as interference, which we learned last chapter. An Italian physicist by the name of Francesco Maria Grimaldi discovered the light phenomenon of light diffraction, which is pretty much light burning across an object. And later on, Dutch physicist Christian Huygens established the wave theory that went against Newton. 100 years or so after Newton, a French physicist named Augustin Jean Fresnel, who claimed that light waves were extremely short in wavelength, which proved light interference existed. And then in 1817, the English physicist Thomas Young declared that the wavelength is 1 mu m, or 1/1,000,000th of a meter. After that point, Newton and his theories were officially disproven, and no one really looked at the corpuscular theory anymore. A few decades later, Einstein emerges as a brilliant physicist and brings about the long-forgotten corpuscular theory of Newton that stated light was in fact a particle. He convinced the scientific community to believe in the dual nature of light as both a particle and a wave. Einstein proved that light is a particle, which are photons, but those photons are actually traveling in a wave-like pattern. Now that was extremely revolutionary in the field of physics, but who's going to argue with the guy who made E equals mc squared possible? Einstein used this theory to further his own theory of quantum mechanics. More specifically, it was focused on his light quantum theory, which said the light's energy is related to its oscillation frequency. This led to Einstein saying that the photons have equal energy to Planck's constant times oscillation frequency. So hypothetically speaking, if the oscillation frequency is 10, then the energy of the photons would be 6.626 times 10 to the negative 33rd. Furthermore, the photon energy is also the height of the oscillation frequency, while the intensity of the light is how bright or dim it is. How bright or dim it is the quantity of the photons itself. So the actual equation that I was talking about is E equals h times f. E equaling energy of the photons, h equals Planck's constant, which is 6.626 times 10 to the negative 34, and then f equaling oscillation frequency. All these properties are virtually invisible to the naked eye unless you have a microscope the size of the Hubble telescope, but other than that, you will not be able to see the photons. Albert Einstein, who is famous for his theories of relativity, also is known for conducting research on the photoelectric effect. The photoelectric effect is when electrons fly out of a metal surface exposed to light, which I will show a little video after this little section. The strangest thing about the photoelectric effect is that the energy of the electrons that fly out of the metal do not change if the light intensity becomes weak or strong, because if light were a wave, more intense light would have caused the photoelectric electrons to fly out of the metal with greater power, which didn't happen. Something else that was very strange was that the photoelectrons multiply when strong light is applied, so extreme, high, dense light. And Einstein then proclaimed and explained the photoelectric effect by saying light was a particle. He then went on to win the Nobel Prize for Physics for discovering and proving that light was in fact a particle. And in this little particle nature of light, I discovered only one major equation which I've shown. And it is E equals h times F, which is just energy of a photon equals Planck's constant, which is h, which is 6.626 times 10 to the negative 34, and that is multiplied to F, which is the oscillation frequency of the light. Other than that, that is all you have to know about the particle nature of light. Thank you.
It can be anything. When you shine light at the surface of a metal, it can be entirely, it will actually jump up out of the metal. Then comes in. Bam! There goes another electron. And the electron's
Nature of light took a long time to become a very well recognized theory, although it was discovered over 300 years ago. That big name that is associated with completely discovering and proving that light is also a particle is Einstein, not Newton, although Newton was initially the first to say it, because he won the Nobel Prize for his efforts to discover light was actually a particle. There was also the photoelectric effect, which I just recently talked about, in which electrons flew out of a metal surface when the metal is exposed to light. And that was really strange because that was what Einstein used to prove his theory of light is a particle, because the electrons bounced off, which was a particle, just showing it was an actual particle. Through all that came about the equation E equals h times F, which allowed for the solving of how much energy the photons had. So, thank you for watching, and I hope you enjoyed this wonderful presentation of The Power of Physics, the Particle Nature of Light edition. Hasta la vista, amigos.